Hello, my name is Ryann Fortner, and this is my presentation of Lab 2 for Physics 2211, Motion of a Falling Object. Firstly, I will go over the purpose and fundamental principles behind this lab. Next, I will outline my design, observations, and my computer models. And finally, I will compare all of my data and answer other relevant questions. The purpose of this lab is to capture an object's motion while falling in order to create two computational models for comparison, one where gravity is the only force acting on the system, and another where gravity and drag influence the system. This lab highlights the differences in velocity and position data when key assumptions are made, such as the exemption of drag compared to the motion that is actually observed. The models become more and more accurate when more forces are included. The first fundamental principle in this lab is Newton's second law, which states that an object in motion will stay in motion until influenced by a force from its surroundings. It is defined most simply by F net equals mass times acceleration. Using the variables definitions, we can manipulate this law to compute the expected velocity or position, which we do in the code for this lab. The second fundamental principle we see in this lab is the acceleration of gravity near Earth's surface, which is assumed constant at 9.8 meters per second squared and always points in the negative y direction due to its attractive nature. Finally, drag force is the force that acts directly against the motion of the object through a substance. And while gravity is directly proportional to an object's mass, drag force is directly proportional to an object's surface area. For this lab, we'll be using a simplified equation for the drag force, where drag force equals negative b velocity squared times v hat. My system is a plush B, and the surroundings are my room. I estimated the mass of my system to be 0.4 kilograms, and it fell approximately 1 meter to the dresser below. The initial velocity is 0, as the system started from rest. Firstly, I videoed my system falling after starting from rest. Then I used Tracker to extract position versus time data, and using this data I created two computational models analyzing gravity and/or drag influence on the system. Finally, I compared my observation data, gravity-only model, and gravity and drag model by combining them onto one graph. Here are the graph and data table from my video analysis and Tracker. I extracted the position data by tracking the center of mass of my system falling from y equals 0 down to y equals 1 meter. Moving on to the computational models, I used the same initial conditions from my Tracker analysis for both codes. The only difference is the inclusion of a non-zero proportionality constant when including drag, which I've found to be 1.2. From there, I also included the basic drag force equation and added it to the gravitational force to find net force. Here's a graph of all of my position and time data. When both drag and gravity are included, the position curve is very shallow. When only gravity is included, the position curve is very steep. The observed position data is somewhere in between. This could mean that there are other forces at play that I am not including. However, there could also be human error at play, as I have little Python coding experience, and I did not have an excess of data from my Tracker analysis. Now on to other relevant questions. What does it mean that the velocity curves differ between the two computational models? The model that includes gravity and drag results in a simplified display of terminal velocity, where the force of the drag perfectly matches the force of gravity in the opposite direction. This leads to a constant speed where no further acceleration is possible due to the drag/air resistance. In this visual from my model, you can see that the orange gravity vector is roughly the same size and length as the blue drag vector, but points in the exact opposite direction. This is a good simplified image of how terminal velocity occurs. As you can see, there is a point where velocity becomes constant on graph 2, whereas graph 1 constantly increases in the negative direction. What if the B was initially thrown downwards? Would that change the terminal velocity? The terminal velocity would not change so long as the object, gravity, and air density stayed the same. Changing the initial velocity simply changes how fast the object reaches its terminal velocity. If the object is thrown faster than its terminal velocity, its speed would decrease until terminal velocity is reached, as drag increases with acceleration. Here, graph 2 has a steeper slope because I changed the initial velocity from 0, showing an increase in acceleration, but the approximate terminal velocity stayed the same. Thank you for watching my presentation.